Let us now see how we will simulate the primary converters. I will supply in the resource portion of the course website the simulation files for the buck, the boost and the buck boost converters. Here what we have discussed everything about the primary converters except that how to give the information signal, the gate pulse signal to the controlled switch. So what I have done here is that I have passed it. I am passing it through a PWM generator block during simulation and giving a voltage which is proportional to duty cycle. So if I want a lower duty cycle, I will decrease the voltage, higher duty cycle, I will increase the voltage, and this will compare with a triangle waveform to generate the PWM, and these signals will turn on this BJT. So inside this PWM block, what you may find is that there is a triangular carrier. So this is, let us say, 10 kilohertz. I have set it to 10 kilohertz for now, but you can experiment with different frequencies. And this carrier is swinging from -1 to +1, and then you can have a control voltage, a voltage which is proportional to duty cycle, and then you will see that after comparison of these two voltage signals, the output that you will get will be something like this. So let us say all the at this comparison point, you will see that the voltage proportional, the control voltage proportional duty cycle is higher. So let us say we will have a high there, and then here the control voltage is lower than the triangle, and here it's higher than the triangle, so on. So as this control voltage moves up and down, you will see a modulation here happening in the pulses, and these are the pulses that will be given to the control, will be used as control signals for Q, and this is what you will be seeing at these points. Later on I will discuss in detail what goes into making the PWM, so that you can build other PWM blocks and techniques. Let us now look at the simulation of buck converter in ngSpice. I'll go into the work folder. In the work folder, I have a folder called buck, and within that there are few files. So there is a buck.cir, buck.net, buck.sch, this is the schematic file, and there is this edt01.sub. This is the file that holds all the library of subcircuits. Forget about this, this is not needed. Now if I open the schematic file, the schematic file is the one which is used to generate the netlist. So I'll open the schematic file. So it looks something like that. It is in GSHM. So let me zoom this. Yes. So this is the buck converter circuit. You have a switch, diode, inductance, capacitance, load, input voltage at 12 volts, and there is a PWM generation block which generates pulse width modulated signal and initiates switch on and switch off of this switch. So here these two components, one is this generic switch which is having first character X, it is a subcircuit, and then there is this block, it's a PWM block, single phase PWM block, which is having also the first character X. This is also a subcircuit. The models for both this generic switch and this PWM block are located inside in this edt01.sub, and this is how it is referenced in the netlist. So if I open the edt01.sub file, you will see the sub-circuit. Let me place it in this fashion here. So there is the diode model, default diode, and this is the power diode model, and you have the power switch. This is the model of the power switch, which is the one which is used here for this IGBT switch, generic switch. And then there is another sub-circuit which is PWM triangle PWM, and this is the sub-circuit for generating the PWM. This is developed using the analog behavioral model part of ngSpice. ngSpice is very powerful, where you can also have analog behavioral model components. They all start with A. See, analog behavioral model, A tri is a triangle generator, compare, A limit, A limiter. So these are analog behavioral models available in ngSpice. Look at its documentation, you will understand how this PWM has been generated, sub-circuit has been generated using the analog behavioral model components. I am passing a parameter NP in, this is the input for the PWM, which sets the duty cycle. NP out is output of the PWM, which gives you the pulse signals, and parameter Fs is being passed. I have set the default at 10 kilohertz, and it can be varied on the fly by passing the parameters for the frequency. So now that we have the sub-circuits, and we have also placed values on the inductance, values on the capacitance, the load, and I also placed some node labels here. A, P, this is node label for output, this is node label for gate drive, which can be used for sensing the potentials at these points. Now let us simulate this schematic. So before we simulate, let us generate the netlist and then go into the ngSpice environment and run the simulation. Let us look at this .cir file. So let me open the .cir file. So it is a transient analysis. 1 microsecond is the step time, and 100 millisecond is the final time. Use initial condition, and it includes the buck.net or the netlist. So within the control commands, control statements, I am setting the background as white, setting the foreground as black, running the simulation, and then plotting the inductor current IL. This is what this particular .cir files, when ngSpice calls this, all these are executed. So let me now delete this netlist. The netlist will get generated afresh. I will delete this netlist and then open the command window. In the command window, I will change directory to the work folder, and in the work folder you see there is buck, so I will change directory to the buck folder, and you will see that we have buck.cir.sch and the sub-circuit file. So let me run the run sim, in which I am having the netlist generator syntax, and followed by it calling ngsim and ngsim for the buck.cir. So I will give this. You will see that the netlist gets generated, and then it goes into the ngsim environment. The simulation is conducted, and the plot IL is plotted here. I can expand this. So this is IL, this is the stable part. So you can, steady state is achieved somewhere here, let us say. A very small portion I am going to zoom in and then see that waveform. So you will see that this is the waveform of the inductor current. So let me see the potential here, Vp. This should be switched, and together with it I will see also the inductor current. We saw inductor current was the order of around 90 milliamps or so, and this potential will be of the order of 12 volts, going from 12 to 0. So if you want to see these two waveforms together, this potential waveform and the inductor current, I will scale the inductor current 100 times and then show it on the display. So let us go to the ngSpice environment, and I will plot Vp and I will plot IL, and I will scale that 100 times so that you will get a comparable graph. I will open that. So the steady state is around this region. So let me expand that, zoom it. So this portion, so you will see this is Vp, which is switching at a given duty cycle, and the inductor current rises when the switch is on, and during this period when the switch is off, the inductor current discharges into the output capacitor and the load. Observe here the duty cycle. I have set the duty cycle comparison. There is a triangle inside and it is compared with this 0.5 volts. The triangle is going from -1 to +1, which means when the compare point is 0, the duty cycle is 50%. When the compare point is 0.5, the duty cycle is 75%, and so on. So therefore, you can observe here that the duty cycle, the on time is 75% and 25% is the off time. Many a times you would like to know what is the effective input resistance as seen from the source. So which means you would like to see what is the source voltage divided by the average current that flows in out of the source. We can easily see that. Let me go to the ngSpice environment. See, plot IV in, but the source current is taken as positive going into the positive terminal. So I will put a minus sign, and you will see that this is the source current. The source current is like this, zoomed up. So during the time when the switch is on, you will see the inductor current portion when the switch is on reflected as the source current. And to find the input resistance, you have to take the average of this current and use it for finding the resistance. You can plot this is the input current and also the average of the input current. So this will give you the input and the average of the input. Around here is the steady state value. So let me zoom it in here. So you will see that this is the input current and this is the average of the input current, and you can use this average of the input current to calculate the input resistance. V in divided by this average value, the current will give you the input resistance of the buck converter circuit under steady state operating conditions for that particular duty cycle. You can plot V naught and V input, which will give an idea of the input output relationship. So this is the input 12 volts and this is the output under steady state conditions. You have the duty cycle around 75%, and you can calculate and find out what is the input output relationship, and authenticate it with theory. And also, if there is a deviation, why is there a deviation, what are the non-idealities which is causing the deviation, all these things can be studied and understood.